Going to read the chapter Ethers and Epoxides of Organic Chemistry from Pardeep's book by Dr. S.N. Dhawan. Chapter 3 Ethers and Epoxides 3.1 Introduction. Organic compounds having COC as a functional group are called ethers. Their general formula is ROR dash, where R and R dash may be same or different alkyl or aryl groups, or one or of them may be an alkyl group and the other aryl group. The divalent oxygen is also called the ethereal oxygen. Ether in which the group R and R dash are the same are called simple or symmetrical ethers, while those in which the groups R and R dash are different are called mixed or unsymmetrical ethers. For example, diethyl ether, diphenyl ether, ethyl methyl ether, methyl phenyl ether. Ethers may be regarded as the functional isomer of alcohols. For example, both dimethyl ether and ethyl alcohol have the same molecular formula C2H6O but different functional groups. 3.2 Classification. Ethers may be broadly classified into the following three categories. First, aliphatic ethers, in which R and R dash may be saturated or unsaturated group derived from aliphatic hydrocarbons. For example, ethyl methyl ether, methyl vinyl ether, divinyl ether. Second, aromatic ethers, in which either one or both R and R dash are aryl groups. For example, methyl phenyl ether, ethyl phenyl ether, diphenyl ether. Aromatic ethers are further subdivided into phenolic ethers and diaryl ethers. Ether in which one of the group is aryl while the other is alkyl are called phenolic ethers or alkyl aryl ethers. On the other hand, ethers in which both the groups are aryl are called diaryl ethers. For example, methylphenyl ether, phenolic ether, diphenyl ether, diaryl ether. 3. Cyclic ether. Ethers in which the oxygen is present in a ring are called cyclic ethers. They are further classified as simple cyclic ethers or crown ethers. Simple cyclic ethers. Cyclic ethers containing 1, 2 or 3 oxygen atoms in the ring are called simple cyclic ethers. For example, oxirane, oxetane, tetrahydrofuran, THF, THP, 1,4-dioxane, 1,3,5-trioxane. Crown ethers. Cyclic ethers containing at least 4 oxygen atoms are called crown ethers because their three-dimensional shape resembled the shape of a crown. They are usually named as X crown Y, where X is the total number of atoms and Y is the number of oxygen atoms. For example, 12 crown 4, 15 crown 5, 18 crown 6. 3.3 Nomenclature. 1. Open chain or acyclic ether. First, common system. The common name of the ether are derived by the naming the two aryl or alkyl groups linked to the oxygen atom in alphabetical order and adding the word ether. In case of symmetrical ethers, the prefix di is used before the name of the alkyl or the aryl group. Some aromatic ethers, however, have their special names. For example, methyl phenyl ether is called anisole or ethyl phenyl ether is called phenol. Second, IUPAC name. In the IUPAC name system, ethers are named as alkoxyalkanes. The ethereal oxygen is taken with the smaller alkyl group and forms a part of alkoxy group, while the larger alkyl group is considered to be a part of alkene. For further illustration, the IUPAC names of some other acyclic ethers are given below. 2-methoxyethanol, 2-chloroethoxyethane, bromoethoxybenzene, 2-methoxy-2-methyl propane, 3-methyl-1-butoxybenzene. Second, acyclic polyethers. Long chains of polyethers are named as oxa-derivatives of the alkane corresponding to the total number of carbons and oxygen atoms present in the chain. For example, 2,5-dioxahexane, 2,5,8-trioxanonane. 3. Cyclic ethers. First, common names. In the common name system, the three-membered cyclic ethers are named as oxides of the alkylene from which they are derived. For example, ethylene oxide or epoxide, propylene oxide, isobutylene oxide. The names of some cyclic ethers are based upon the names of their fully hydrogenated products. For example, furan plus 2H2 is equal to tetrahydrofuran. 2H-pyran plus 2H2 is equal to tetrahydropyran. IUPAC names. The IUPAC names of cyclic ethers CH2O whole power n, where n is equal to 2, 3, 4, 5 and 6 as given below. N is equal to 2 oxyrane, N is equal to 3 oxytane, N is equal to 4 oxolane, N is equal to 5 oxane, N equal to 6 oxypane. The italicized portions of these names are the suffixes used to represent the size of saturated heterocyclic rings other than the N atoms. In case of substituted cyclic ethers, the substituents are indicated by numerical prefixes with oxygen. And getting number 1. Trans 2,3 dimethyl oxyrane, 3,3 dichloro 2 methyl oxytane, cis 2 chloro 6 ethyl oxypane. 3.4 Methods of formation. Ethers can be prepared by the following general methods. First, from alkyl halides. First, Williamson's synthesis. This is one of the best method for the preparation of ethers. It involves the treatment of an alkyl halide with a suitable sodium alkoxide. The sodium alkoxide needed for the purpose is prepared by the action of sodium on the suitable alcohol. The reaction, in fact, involves the nucleophilic displacement of the halide ions from the alkyl halides by the alkoxide ion by SN2 mechanism. Thus, 2ROH plus 2Na is equal to 2RONA positive plus H2. This method can be used for the preparation of both symmetrical and unsymmetrical ethers. For example, sodium ethoxide plus ethyl bromide is equal to at 330 Kelvin is equal to diethyl ether. Sodium butoxide plus methyl bromide at given heat is equal to butyl methyl ether. Similarly, alkyl aryl ethers, that is phenolic ethers, can be easily prepared by treating sodium phenoxide with alkyl halides. For example, sodium phenoxide plus methyl bromide is equal to Nasol plus Na positive Br negative. Like halide ions, sulfate ions is a good leaving group. Therefore, a Williamson's synthesis alkyl halide may be replaced by alkyl sulfates. For example, sodium ethoxide plus dimethyl sulfate is equal to ethyl methyl ether plus Na2SO4. Limitations. A proper choice of alkyl halide and sodium alkoxide to be used in Williamson's synthesis is necessary in view of the following considerations. First, since a halogen attached to a double bond or an aromatic ring cannot be readily displaced by a nucleophilic reagent, therefore, aryl halides are not generally used in Williamson synthesis. Therefore, for the synthesis of simple alkyl aryl ethers, the reaction is carried out between an alkyl halide and sodium phenoxide and not between aryl halide and sodium alkoxide. For example, sodium phenoxide plus ethyl iodide at given heat is equal to phenitol. Bromobenzene plus sodium ethoxide is equal to no reaction. However, if the halogen is activated by the presence of electron withdrawing group at O and para position, with respect to halogen atoms, such activated aryl halides can be used in Williamson synthesis. For example, p-nitrobromobenzene plus sodium ethoxide is equal to p-nitroanisole. Second, we have stated above that Williamson synthesis involves the nucleophilic attack of the alkoxide phenoxide ions on alkyl halide. Now, depending upon the structure, alkyl halides may undergo substitution or elimination reaction. Therefore, for the success of this reaction, it is essential that the alkyl halide used must be such which predominantly undergoes nucleophilic substitution. Since primary alkyl halides are more susceptible to SN2 reactions, therefore best yields of unsymmetrical ethers are obtained when alkyl halides are primarily and alkoxides may be primary, secondary or tertiary. For example, butyl ethyl ether is prepared by treating ethyl bromide with sodium butoxide. Sodium butoxide plus ethyl bromide at heat gives butyl ethyl ether plus Na positive Br negative. The above ether cannot be prepared by treating sodium ethoxide with butyl chloride or bromide. Since under this condition an alkene, that is isobutylene, is the main product. With secondary alkyl halides, both substitution and elimination occurs together, giving a mixture of ethers and alkenes. But with tertiary alkyl halides, only elimination occurs, giving alkenes. Thus, when a mixture of butyl bromide is treated with sodium ethoxide, butyl ethyl ether is not formed, but instead 2-methylpropane is formed due to elimination reaction. Butyl bromide plus sodium ethoxide at heat gives 2-methylpropene plus ethanol plus NABR. Due to steric hindrance, secondary alkyl halides also prefer to undergo elimination rather than substitution. For example, 2-bromopropane at 300 plus sodium ethoxide at 330 Kelvin gives propene 79% to ethoxypropene 21%. Second, reaction with alkyl halide with dry silver oxide. Ethers can also be prepared by heating an alkyl halide with dry silver oxide. For example, ethyl bromide plus Ag2O at given heat gives diethyl ether plus 2 AgBr. Second, from alcohols. Ethers may be prepared from alcohols as follows. First, by dehydration of alcohols. Ethers may be prepared by dehydration of alcohols either in the presence of acid or heated alumina. A. Acid catalyzed dehydration. Symmetrical ethers can be prepared by dehydration of alcohols with concentrated H2SO4 at 413 Kelvin. ROH plus ROH at concentrated H2SO4 413 K gives ether plus H2O. For example, ethanol at concentrated H2SO4 at 413 Kelvin gives diethyl ether plus H2O. The yield of ether, however, depends upon the nature of alcohol, whether 1 degree, 2 degree or 3 degree. Since in this reaction 2 molecules of alcohol lose 1 molecule of water, therefore, it is better called an intermolecular dehydration. Limitations. Though this method is useful for the large-scale production of ethers, it has two major drawbacks. First, the preparation of ethers is always accompanied by the formation of alkene due to intramolecular dehydration of alcohols. However, in case of 1 degree alcohol, the alkenes are formed only to a small extent, which can be further suppressed by using a large excess of the alcohol. In case of 2 degree alcohols, alkenes are formed in much large amounts than ethers, but in case of 3 degree alcohols, exclusive formation of ethers occur. Thus, the order of dehydration of alcohols leading to the formation of ethers follows the sequence: primary is more than secondary is more than tertiary. Therefore, dehydration of alcohols is used only for preparing ethers from primary alcohols. Second, this method is not suitable for unsymmetrical ethers because a complex mixture of ether is always obtained. For example, 3ROH plus 3R-OH at concentrated H2SO4 gives ROR plus ROR- plus R-OR- plus 3H2O. Mechanism. This reaction is an example of a nucleophilic substitution reaction in which protonated alcohol molecule acts as a substrate, water as a leaving group, and another molecule of alcohol as a nucleophile. The reaction may follow either first order kinetics or second order kinetics, depending upon the nature of alcohol used. In general, 1 degree alcohol follows SN2 mechanism, while 2 degree and 3 degree follows SN1 mechanism. B. Catalytic dehydration. Dehydration of alcohols from ethers can also be achieved by passing the vapors of an alcohol over heated alumina at 523 Kelvin. For example, ethyl alcohol is equal to in presence of Al2O3 and 523 Kelvin diethyl ether plus water. Second, by the action of diazomethane or alcohols on alcohols or phenols. Methyl ethers can also be prepared in excellent yields by the action of diazomethane CH2N2 on alcohols on or phenols in presence of tetrafluoroboric acid HBF4 as catalyst. For example, tetrafluoroboric acid plus diazomethane is equal to CH3N positive triple bond and BF4 negative. Ethyl alcohol is equal to minus N2 minus BF4 negative is equal to ethyl methyl ether. Third, from alkenes. Ether can be prepared from reactive alkenes by the following two methods. First, direct addition of alcohols in presence of acids as catalyst. For example, 2-methyl propene plus methanol in presence of H2SO4, that is Markovnikov's addition, gives 2-methoxy 2-methyl propane. The main disadvantage of this method is that sometimes the initially formed carbocation rearranges the most stable carbocation, which then reacts with alcohol to form rearranged ethers. For example, 3,3-dimethyl 1-butane in presence of H2SO4 gives 2-ethoxy 2,3-dimethyl butane rearranged product and 3-ethoxy 2,2-dimethyl butane normal product. Second, indirect addition of alcohols, alkoxy mercuration reduction. Alkenes readily react with mercuric trifluoroacetate in the presence of an alcohol to give alkoxymercurial compounds, which upon reduction with NaBH4 in basic mediums gives ether in high yields. For example, propene plus mercuric trifluoroacetate gives 2-ethoxypropene. This two-step process is called alkoxymercuration reduction or alkoxymercuration demercuration and gives ethers in accordance with Markovnikov's addition of alcohols to alkenes. The main advantages of this method over Williamson synthesis are: first, the reaction does not involve carbocation intermediates and hence there is no rearrangement in this reaction. 3,3-dimethyl 1-butene plus ethanol in presence of first HgOOCCF3 twice, second NaBH4OH negative gives 3-ethoxy 2,2-dimethyl butane. Second, in absence of competing elimination reaction. Fourth, from Grignard reagents. Higher ethers can be prepared by treating alpha halo ethers with suitable Grignard reagents. For example, methoxychloromethane plus CH3MgI in presence of dry ether gives ethyl methyl ether plus chloromagnesium iodide. 3.5 Physical properties. First, physical state, color, and odor. Dimethyl ether and ethyl methyl ethers are gases at ordinary temperature, while the other lower homologues of ethers are colorless liquids with characteristic ether smell. Second, dipolar nature. Because of the greater electronegativity of oxygen than carbon, the CO bonds are slightly polar and thus have a dipole moment. Since the two CO bonds in ether are inclined with each other at an angle of 110 degrees, the two dipoles do not cancel each other. As a result, ethers have dipole moment of 1.15 to 1.3 d. For example, the dipole moment of dimethyl ether is 1.3 d and that of diethyl ether is 1.18 d. 3. Boiling points. Ethers are isomeric with monohydric alcohols, but their boiling points are much lower than the isomeric alcohols. This is due to the reason that unlike alcohols, ethers do not form hydrogen bonds. As a result, ethers do not show molecular association and hence have lower boiling points than corresponding alcohols. Further, the weak polarity of CO bonds does not appreciably affect the boiling points of ethers, which are about the same as those of alkanes with comparable molecular masses. Fourth, solubility. Ethers containing up to 3 carbon atoms are soluble in water. The solubility of other lower ethers in water is comparable to those of corresponding alcohols. For example, like ethanol, dimethyl ether is completely miscible with water. Similarly, both diethyl ether and N-butyl alcohol are soluble in water to a small extent, that is 8 gram per 100 gram of water. The solubility of lower ethers in water is due to the formation of hydrogen bonds between water and ether molecules as shown below. As the molecular mass increases, the solubility of ethers in water decreases due to a corresponding increase in the hydrocarbon portion of the molecule. Ethers are, however, fairly soluble in common organic solvents such as alcohol, benzene, chloroform, acetone, etc. 5. Density. All ethers are lighter than water. 3.6 Chemical properties. Ethers are relatively inert compounds, almost as inert as alkenes. Under ordinary conditions, they are stable to bases, dilute acids, catalytic hydrogenation, and to most other reducing agents. This is due to the reason that the functional group of ethers does not contain any active site in their molecule, as compared to hydroxyl group of alcohols and phenols, even though the oxygen atom in both these functional groups contains two lone pairs of electrons. However, under specific conditions, ethers undergo the following reactions. First, reaction of the ethereal oxygen. On account of the presence of two lone pairs of the electrons on the oxygen atom, ethers behaves as Lewis bases and thus undergo reactions involving the formation of coordinate bonds, as discussed below. First, action of concentrated acids. Formation of oxonium salts. The oxygen atom in ether has two lone pairs of electrons. As a result, ethers behaves as Lewis bases and thus dissolve in cold concentrated inorganic acids to form stable oxonium salts. For example, ether is converted into dialkyloxonium chloride. Example, dimethyl ether is converted into dimethyl oxonium chloride. Diethyl ether is converted into diethyl oxonium hydrogen sulfate. Second, formation of coordination complexes. Being Lewis bases, ethers form coordination complexes known as etherates with Lewis acids such as BF3, AlCl3, FeCl3, Grignard reagents, etc. Diethyl ether plus BF3 is equal to boron fluoride etherate. 2-diethyl ether plus Grignard reagent is equal to Grignard reagent etherate. Due to the formation of the complexes, Grignard reagents dissolved in ether. That is why Grignard reagents are usually prepared in ethers. They, however, cannot be prepared in benzene because benzene has no lone pairs of electrons and hence cannot form complexes with them. Second, reactions involving the cleavage of carbon-oxygen bond. First, with halogen acids, ethers are readily cleaved by hydrodic acid and hydrobromic acid at 373 Kelvin to form an alcohol and an alkyl halide. For example, ether at 373 K gives alcohol plus alkyl halide. Diethyl ether plus HI at 373 K gives ethyl iodide and ethyl alcohol. However, if excess of acid is used, the alcohol first formed reacts further with the halogen acid to form the corresponding alkyl halide. ROH plus HX at 373 Kelvin is equal to RX plus H2O. The overall reaction may then be written as ROR plus 2HI at 373 Kelvin is equal to 2RI plus H2O. Diethyl ether plus 2HI is equal to at 373 Kelvin is equal to ethyl iodide plus H2O. Similarly, cyclic ethers are readily cleaved by HBr or HI to yield dihaloalkenes. For example, THF plus 2HBr at 373 K gives 1,4-dibromobutane plus H2O. Reactivity of halogen acids. The order of reactivity of halogen acids follows the sequence HI more than HBr more than HCl. As discussed above, the cleavage of ethers by halogen acids in fact involves the nucleophilic attack of the halide ion on the protonated ether molecule. Obviously, greater the nucleophilicity of the halide ion, more reactivity of the halogen acid. Since the nucleophilicity of halide ion follows the sequence I negative is more than Br negative is more than Cl negative. Therefore, the reactivity of the halogen acids follows the same sequence, that is Hi is more than Br is more than HCl. Mechanism. The cleavage of ethers by halogen acids occur by the following mechanism. Step 1. Ethers being Lewis bases undergo protonation to form oxonium salts. Second, the protonated ethers thus formed undergoes nucleophilic attack by the halide ion, either by SN1 or by SN2 mechanism, depending upon the nature of the groups R and R' and the reaction conditions, to form a molecule of an alkyl halide with the displacement of the weakly basic alcohol molecule. If the groups R and R' are primarily, the reaction occur by SN2 mechanism, and if the secondary or tertiary, the reaction occurs by SN1 mechanism. Site of cleavage. The site of cleavage of unsymmetrical ethers by halogen acid depends upon the nature of the group R and R'. The following cases arises. First, if both of the groups R and R' are primarily, the alkyl halide is always obtained from the smaller alkyl group. For example, ethyl methyl ether at 373 K gives methyl iodide plus ethyl alcohol. Second, if one group is methyl and the other is a 1 degree or 2 degree alkyl group, the reaction occurs by SN2 mechanism. Due to steric hindrance, the halide ion always attacks the smaller alkyl group, that is CH3 group, to give methyl iodide, while the bulkier alkyl group gives the alcohol. For example, methyl isopropyl ether plus concentrated HI at 373 K gives methyl iodide plus isopropyl alcohol. Third, if one group is methyl and the other is a tert alkyl group, the reaction occurs by SN1 mechanism, and the formation of the product is controlled by the stability of the carbocation resulting from the cleavage of CO bond in protonated ether. Since tert alkyl carbocation is much more stable than methyl carbocation, therefore the alkyl halide is always derived from tert alkyl group, and the alcohol forms the smaller group, that is methyl group. For example, tert butyl methyl ether in presence of concentrated H2SO4 at 373 Kelvin gives tert butyl iodide plus methyl alcohol. It may be emphasized here that the high polarity of the solvent H2O present in concentrated HI 57% has favored SN1 mechanism. However, if the cleavage of tert butyl methyl ether is carried out in anhydrous HI in ether, the low polarity of the solvent ether would favor SN2 mechanism, and hence I negative ion will attack the less hindered methyl group, giving methyl iodide and tert-butyl alcohol. Tert-butyl methyl ether in presence of anhydride HI or ether mechanism gives methyl iodide plus tert-butyl alcohol. Fourth, cleavage of alkyl aryl or diaryl ethers. In case of the alkyl aryl ethers, the products are always phenol and an alkyl halide and never an aryl halide to an alcohol. For example, methyl alcohol anisole at HI and 373 Kelvin gives phenol plus methyl iodide and not methyl alcohol plus iodobenzene. The carbon atoms of the phenol group are sp2 hybridized while that are of aryl group are sp3 hybridized. A sp2 hybridized carbon being more electronegative repels the nucleophilic while a sp2 hybridized carbon being less electronegative attracts the nucleophile. In other words, nucleophilic attack by the halide ion occurs more easily on the alkyl group, leading to the formation of an alkyl halide and phenol. Secondly, a phenyl group is much bigger in size than an alkyl group. Therefore, because of steric hindrance of the bigger phenyl group, the halide ions attack the alkyl group, leading to the formation of an alkyl halide and phenol. It may, however, be noted that phenol is not converted into iodobenzene even with excess of HI. Diaryl ethers are not cleaved by HI because both of the carbon atoms to which oxygen is attached are sp2 hybridized and hence repel the nucleophilic halide ions. Ziesel method. Cleavage of alkyl aryl ethers by hydriodic acid HI forms the basic of Ziesel method for the estimation of alkoxy groups such as methoxy or ethoxy group in such ethers. A known weight of a phenolic ether is treated with an excess of concentrated hydriodic acid. The alkyl iodide produced as a result of cleavage by ethers by HI is treated with an ethanolic solution of silver nitrate. The precipitate of silver iodide thus formed is filtered, washed, dried and weighed. From the amount of AgI formed, the percentage of alkoxy group can be estimated. Second, with sulfuric acid. On heating with dilute sulfuric acid under pressure, ethers are hydrolyzed to alcohols. Ether in presence of dilute sulfuric acid under pressure gives alcohol. Diethyl ether plus water under dilute sulfuric acid gives ethyl alcohol. Second, when heated with concentrated H2SO4, ethers react in the same manner as the halogen acids to form an alcohol and an alkyl hydrogen sulfate. For example, diethyl ether with concentrated H2SO4 gives ethyl alcohol plus ethyl hydrogen sulfate. Secondary and tertiary ethers, however, form alkenes. Tert-butyl methyl ether in presence of concentrated H2SO4 gives isobutylene plus methanol. Third, reactions involving the alkyl group. First, action of air and light. Auto-oxidation. Formation of peroxides. When exposed to air and light for a long time, ethers are oxidized to form hydroperoxides or simply peroxides. Diethyl ether in presence of light and O2 gives 1-ethoxyethyl hydroperoxide. It is a free radical reaction and oxidation occurs at the carbon atom next to the ethereal oxygen to form hyperoxides. These peroxides are very dangerous compounds since they decompose violently at high temperatures. Therefore, serious explosions may occur during distillation of old samples of ethers if peroxides are not removed. Presence of peroxides in old samples of ethers may be detected by shaking them with a freshly prepared solution of FaSO4 followed by addition of KCNS. Appearance of red color indicates the presence of peroxides. A simple method to remove peroxides is to shake an old sample of ether with either an aqueous solution of Ki or a ferrous salt. When ether peroxides are reduced to ether and I negative ion is oxidized to I2 or Fe2 positive salt is oxidized to Fe3 positive salts. Second, halogenation. Either ethers react with Cl2 or Br2 to give substitution products. The extent of halogenation, however, depends upon the reaction conditions. For example, diethyl ether reacts with chlorine in the dark to give alpha-dichloro diethyl ether. Diethyl ether in presence of Cl2 dark gives alpha-dichloro diethyl ether. It goes on Cl2 and dark gives alpha-dichlorodiethyl ether. However, in the presence of light and excess of chlorine, all the hydrogen atoms are substituted to give perchlorodiethyl ether. Epoxides. Three-membered cyclic ethers are called epoxides. In the common system, they are called alkoxy but in IUPAC system name they are called either alkene oxides, for example ethylene oxide, 2,3-butene oxide, 3.7. Synthesis of epoxides. There are two main laboratory methods for the synthesis of epoxides. These are: first, epoxidation of alkenes. Alkenes on treatment with peroxides all are called peracids. Perbenzoic acid, M-chloroperbenzoic acid, etc. in an inert solvent such as CH2Cl2, CHCl3 or CCl4 give epoxides. Due to the formation of epoxides, the oxidation of alkenes with peracids is commonly known as epoxidation. For example, alkene plus peroxy acid in presence of CCl4 gives epoxide. Ethylene plus peroxybenzoic acid in presence of CCl4 gives ethylene epoxide or benzoic acid. 2-methyl-butene in presence of C6H5COOH in presence of CCl4 gives 2,2,3-trimethyloxyrane plus C6H5COOH. Cyclohexene plus M-chloroperoxybenzoic acid in presence of CH2Cl2 at 278 Kelvin gives 1,2-epoxycyclohexane. Mechanism. Peroxy acids act like electrophiles and the reaction is believed to proceed by the following mechanism. Ethylene plus peroxybenzoic acid in presence of CCl4 gives ethylene epoxides plus benzoic acid. 2. From halohydrins. When halohydrins prepared by addition of hypohalous acids to alkenes are treated with a base, HX is eliminated and an epoxide is formed. For example, ethylene in presence of Cl2 and H2O gives ethylene chlorohydrin plus KOH gives ethylene epoxides plus KCl plus H2O. Cyclohexane in presence of Br2 plus H2O gives 2-bromocyclohexanol. In presence of dilute NaOH gives 1,2-epoxycyclohexane plus NaBr plus H2O. Mechanism. It may be noted that the synthesis of epoxides by base treatment of halohydrins is actually an intramolecular Williamson synthesis. Bromohydrin in presence of NaOH gives epoxides. Manufacture of ethylene oxide. It is manufactured by passing a mixture of ethylene and air under pressure over silver catalyst at 573 K. Ethylene plus O2 in presence of Ag and 5 at 573 K gives ethylene oxide. 3.8. Chemical reactions of epoxides. Acyclic ethers and cyclic ethers containing 5 and 6-membered rings such as tetrahydrofuran and 1,4-dioxane are quite inert and are often used as solvents. 3-membered cyclic rings, that is epoxides, on the other hand, are highly reactive. This is due to the reason that 3-membered rings are highly strained, that is, they have considered angle strain. Because of their highly strained natures, epoxides ring can be opened by a variety of nucleophilic reagents under much milder conditions. Consequently, most of the reactions of epoxides are the ring opening reactions. These can be catalyzed both by acids and bases. First, acid catalyzed ring cleavage of epoxides. Due to the large angle strains, epoxides are readily hydrolyzed by dilute mineral acids at room temperature to form corresponding 1,2-diols or glycols. For example, ethylene epoxide plus H2 in presence of H positive gives ethylene glycol. Similarly, halogen acids and alcohols in presence of acids can bring about the cleavage of epoxides. Ethylene oxide plus HBr gives 2-bromoethanol. Oxyrane plus ethanol in presence of H positive gives 2-ethoxyethanol. Mechanism. In the acid catalyzed hydrolysis of epoxides, the oxygen atom of the epoxide ring first accepts a proton to form protonated epoxides. The protonated epoxides then undergoes nucleophilic attack SN2 by water to give a trans 1,2-diol. Second, base catalyzed ring cleavage epoxides. Unlike ordinary ethers, epoxides can also be cleaved under basic conditions. Ethylene oxide plus water in presence of OH negative gives ethylene glycol. Similarly, sodium alkoxides, ammonia or amines can also bring about cleavage of the epoxide ring. Sodium methoxide in presence of epoxide gives 2-methoxyethanol mechanism. Due to greater electronegativity of oxygen than carbon, the carbon atom of the epoxide ring carries a small positive charge and hence can be easily attacked by strong nucleophilics such as hydroxide, alkoxide, phenoxides, ammonia, amines, etc. Stereochemistry of ring cleavage of epoxides. Both acids and bases catalyzed ring opening reactions of epoxides occur by Sinto mechanism. Therefore, attack of nucleophilic always occurs from the backside, leading to the formation of a trans 1,2-diol. 3. Reaction with Grignard reagent and organolithium reagents. Epoxides also undergo ring opening reactions with Grignard reagents and organolithium compounds. The addition products initially formed upon hydrolysis gives primary alcohols containing two carbon atoms more than the Grignard or the organolithium compounds. The epoxide generally used in these reactions is ethylene oxide. Phenyl magnesium bromide plus ethylene oxide in presence of dry ethers addition products gives H positive plus H2O gives 2-phenyl ethanol. Thank you.